Hello everyone, I'm Yujin, and this video presentation is for HapticGen, Generative text-to-vibration model for streamlining haptic design. Kevin and I are co-first authors, with Sang-ho Yoon and Hesti Seifi as corresponding authors. Imagine you're playing VR game. You're playing violin, an epic battle against an alien, or even fishing in a virtual reality. Now, imagine having to create all these sensations from scratch. Coding waveforms, tweaking parameters, and constantly testing. It's a long iterative cycle. So, our HapticGen changes this demanding process by letting anyone simply type a text prompt. Like here, both fencers engaged in a tense blade battle, neither willing to give an inch. And our system instantly generated a convincing vibration pattern. Now introducing HapticGen, the first generative text-to-vibration model that lowers the barriers, fosters creativity, and accelerates workflows. On the left, you might see a short text prompt. Actually, you can put any text prompt from any scenario that you might want to bring into life through tactile feedback. And our model uses a large language model, which is LLM, to generate multiple prompts variants based on the initial description. To train our text-to-vibration model, we collected two key datasets. The first one is the converted audio to haptic signal dataset, and the second one is an expert voted haptic dataset. And our system translates each textured prompt into a few corresponding vibration signals. And you might quickly browse through the generated haptic signals, select them, and play them back on VR controllers. And once you're satisfied, you can export these signals in various XR scenarios. This rapid loop helps users quickly explore lots of ideas. We actually started our process by conducting a design workshop with 9 haptic researchers to explore whether and how current Gen AI tools can be used for haptic design. And we found several limitations to using existing AI tools. And we actually tackled them down in HapticGen by developing 2 large captioned haptic datasets, training and evaluating the text-to-vibration model, and building user interfaces. We developed our model through 6 key steps: developing initial haptic datasets, training a generative model, building a user-friendly interface, curating expert feedback, fine-tuning based on this feedback, and finally evaluating the system. We started by converting the WaveCaps data, which has around 335,000 captioned audio samples, into the vibrations. We chose this dataset because it's large, diverse, and well-labeled, helping us to overcome the scarcity of the haptic dataset. Then we actually filtered out samples containing any speech audio, because speech-related audio typically doesn't translate efficiently into viable tactile feedback. Next, we augmented our dataset with haptic labels by automatically generating tactile-focused captions using LLM. Finally, we converted existing audio files into viable tactile signals, which is optimizing their intensity and the timing for effective haptic perception. And this is our pipeline. It ensures that HapticGen efficiently transforms simple textured prompts into nuanced, realistic vibration outputs. First, we encode the converted viable tactile signals using haptic encoder, compressing them into a compact representation. And at the same time, the user's text prompt is processed by a pre-trained language model, here is T5 large, to extract meaningful textured features. Both encoded viable tactile feedback and text features are then passed into a transformer-based language model. It is adapted from MusicGen architecture, and this transformer learns the relationship between text descriptions and corresponding signals. And the output is decoded using the haptic encodec decoder. And finally, we normalize and decoded signals to ensure consistent perceptible intensity and quantize them into an 8-bit format, which is suitable for playback on haptic devices. And this is our HapticGen UI. When you put the prompt and click the Generate button, you might see generated multiple haptic signals. These files are automatically saved into local folder and displayed as a list on the left side of the UI for easy access. You can immediately see the waveform of the selected signal and simultaneously fill it through the VR controllers. You can also easily indicate the match between the user prompt and each vibration signal using a simple thumbs up and down, helping you quickly indicate like or dislike. After building this initial version, we invited haptic experts to create an expert voted preference dataset by rating the signals. We actually invited a total of 15 experts, including 4 industry professionals and 11 researchers. Each expert has more than a year of experience in haptic design and research. During the 70-minute sessions, they prompt the initial model and rated generated vibrations. Expert voted haptic dataset contains 0.3K data points of signals, user prompts, and votes. Then we moved on to optimization stage, where we fine-tune HapticGen model. We fine-tuned it using the feedback and the data collected from the experts. And finally, we ran a comprehensive evaluation to confirm these improvements. We used the state-of-art text-to-audio generative model for the baseline, combined it with an audio-to-vibration conversion step as well. Let's take a look. We conducted an A/B testing session to evaluate our performance. In total, 32 participants are joined, spending around 75 minutes each in the session, and they were evenly split between experts and novice, included diverse backgrounds to ensure broad perspective. And then we have a total of 5 different themes by creating and evaluating signals. Their ratings and feedbacks also created a user-voted data set as well, containing over 3,200 viable tactile signals. For each theme, like emotion, we took an original prompt. For example, here, the frustration of lying awake in bed as you toss and turn, and generated 4 additional variant prompts. This variance actually helped participants explore subtle differences and identify more precise and expressive feedback. While our model HapticGen effectively captured the intended feeling of the original prompt, the baseline model often struggled to do so. Including simulation and emotion, participants created diverse prompts across 5 distinct themes: sports, interaction, game as well. This allowed us to evaluate how effectively our model performed across various XR scenarios. Participants also mentioned giving more detailed prompts or emphasizing rhythm helps generate better vibration. And they also appreciated that our model produced more varied and nuanced vibrations, which closely matched what they had imagined. Some even mentioned it felt like the system was translating their thoughts directly into tactile sensation. However, there were limitations, especially when participants asked for precise or repeated vibration patterns. This is something that we will address in the future work. Participants actually rated their system significantly higher than the baseline in several key metrics like autotelics, realism, workload, future use, and goal. It shows clear benefits of using HapticGen. So in conclusion, our model HapticGen produced more natural and nuanced vibration than the baseline. I'll say HapticGen marks a step forward in AI-driven haptics. Integrating text-to-vibration generation, user feedback, and large-scale data makes haptic design more intuitive and more efficient. Trained model and haptic datasets are open source right now. So by sharing these resources, we aim to encourage future researches and accelerate advancements in haptic design. So please visit hapticgen.hci.org or feel free to contact us. Finally, I would like to thank all my collaborators. This project was made possible thanks to their support and contributions. And thank you all for your attention.